All right, I think we're good to go. Hi, everyone. Welcome to the Machine Learning and Data Science track for the afternoon sessions. And our first speaker is Frederick Reis, and he will be talking about natural language processing with Pandas DataFrame.
Thank you, Papa.
Reis.
So let me share my screen here. Is that coming through okay? Great.
Yes.
I love these little thumbs up buttons. Okay. So as Fatma mentioned, I'm Fred Reis. I work for IBM specifically. Let me make these slides go full screen here. Specifically, I work for IBM Research, and I also have a joint appointment with our open source side of IBM with the Center for Open Source Data and AI Technologies, which is an open source lab in San Francisco. And the project I'm going to be talking to you today about kind of straddles those two roles, but it's very much in my primary area of research, which is natural language processing. I've been working on NLP since about 2007 on and off. And so in the last 14 years, a lot of things have changed in that field, but one thing really has remained constant, which is that in natural language processing, the easy things are hard. The hard things are easy, but the easy things are hard. Now, let me try and explain this with an example, but first we'll need a little bit of background about the problem area I'm going to be talking about. So one of the most common applications, one of the oldest applications of natural language processing is that of finding facts about people from text. Facts like the fact that Joe is the author of this document, or that this other document is expressing some positive sentiment towards Amy, or that this third document says Lois just traveled to California. And a common way to find these facts about people in text is to follow a three-step process where you run two models and then combine the results. First, you run a model to find mentions of people in your document. Then you run another model to extract out useful facts, like this part of the document is the author list of the document, if you're looking for Joe being the author of the document. Then you match the results of those two models. And if you look at these three steps in this general problem of finding facts about people in text, that first step and the second step are both very hard problems, depending on exactly what variation of finding people and finding facts. You'll find that it maps to a problem like named entity recognition or a NAFRA resolution for people, or structure identification, sentiment analysis. Lots of terms with many syllables that are so long because these are sub-areas of natural language processing research that hundreds of people have spent their entire careers devoted to just that problem. So steps 1 and 2 in this three-step process are super hard. But step 3, that's easy. You're just matching the results of two models. You got two sets of model results, find where they match up. But in natural language processing, the easy things are hard. Let's look at a more concrete example of finding facts about people in text. And I'm going to look at finding the executives of companies in corporate press releases. So our target text is a corporate press release, and we're trying to figure out that somebody is an executive in a company. And a common pattern that you can look for to determine that someone's an executive is that somebody is quoted by name in a press release. Because if someone's quoted by name in a corporate press release, that usually means they're authorized to speak on the behalf of their employer in an official capacity. So you're looking for the picture that we're seeing here, where there's a quote, and inside of the quote, there's a mention of a person by name. And this maps nicely to our three-step process. You have a model that finds people. You have a model that finds the fact that somebody said something. Combine those two models together, and you've got names of executives, right? Let's look at how this breaks down into the individual concrete steps if you wanted to implement matching this pattern. So step 1 is find mentions of people. In this case, we're looking for people mentioned by name, so that's called named entity recognition. That's a hard but well-studied problem in natural language processing. And you can find many open source implementations of this. For example, here's a model from the Hugging Face Transformers library, and that does named entity recognition. And basically with 4 lines of Python code, you can write a program that takes in natural language text and outputs the locations where that text mentions people by name. It's just 4 lines of code. Load the model, run the model, get the results, filter the results, and you're done. So it's hard, but it's easy. Second step is also a hard problem, arguably an even more difficult problem known as semantic role labeling. That's a fairly long term, but basically you need to be able to extract all the things that happen in the document, all the subject, the verb to say. We're looking for instances of somebody said something. That's semantic role labeling. But there are many commercial implementations of semantic role labeling that you can pull off the shelf. Here we have example code for using IBM Watson natural language and semantic role labeling model. And again, it's 4 lines of Python code. The lines are somewhat longer, but it's 4 lines of code. We load the model for you, so you don't need to do that. But you need to run it, you need to filter the results, and then add some location information to enable step 3. So again, this super hard problem becomes easy because there are off-the-shelf packages for it. But what about this third step? Just cross-referencing the results of these 2 models. Well, here's what the code for that looks like. You'll notice it's quite a bit more code. In fact, the font is probably so small it's hard for you to read, but here's the short version. If you just naively compare the results of these 2 models, you would have an algorithm that was quadratic in the size of your document, which would be bad. So you need to divide the document into chunks and build a lookup table for each of the chunks, and then insert one of these sets of model results into the lookup table, probe into the lookup table with the other set of results, find all, this gives you a filtered set of spans that could match, then you compare those pairwise, construct a result record for each one, remove duplicates because something could have hashed into 2 entries of the lookup table, and then you're done. So yes, in natural language processing, the easy things are hard. And I've just shown you one example of an easy step in an NLP application that turns out to be the most difficult one to implement and process. In this case, we're talking about the first one on this list, building an application that combines multiple models together. There are a number of related tasks that you'll see in any end-to-end natural language processing application, things like computing model accuracy or creating and curating training data, debugging your models, that are supposed to be easy because they're not like core NLP research problems, but they end up being really hard in practice. And what these things have all in common is that they're all about analyzing data. They're all about analyzing machine-readable data that your models have pulled out of the natural language text. And we as a discipline, natural language processor practitioners and researchers, have a problem that when we attack these data analysis problems, we have a habit of inventing our own data structures and then inventing our own algorithms to go on top of these data structures, which results in a lot of very unnecessarily difficult, wasted work. Well, if you look at the rest of data science, there are tools, general purpose tools for analyzing data, specifically Pandas DataFrames, that make analyzing data easy. They make data analysis tasks easy. And if you take away one thing from today's talk, it should be that if you're doing natural language processing, you should be using Pandas. You should be using Pandas to make all of these data science, data analysis tasks that would normally be quite challenging because you're inventing your own algorithms and data structures, to make them a lot easier by leveraging 3 aspects that Pandas brings to the table for any data analysis tasks, specifically transparency, simplicity, and compatibility. I'd like to switch to a quick demo that will kind of bring this point across, hopefully. So here I have 2 notebooks. We're going to be covering the same use case that I talked about earlier, where we have, in this case, we have a IBM press release, and we're going to run 2 models and combine the results together of those models so that we can extract out the names of executives from this press release. You can see, for example, here in the 3rd paragraph, we have a long quote from an executive who's mentioned by name. We want to find that pattern by combining the results of 2 models. And I've pre-run the 2 models on this document, and I've got 2 versions of this. On the left, we're going to do this without Pandas. On the right, we're going to do this with Pandas. Okay, so here we have the model, the output from our semantic role labeling model, the model that found instances of the pattern someone said something. And you can see that's, yeah, that's JSON data. Let's see what that looks like as a data frame, as a Pandas data frame. That's a lot simpler. I think we can all agree, if you're going to be looking at something and not trying to understand it, you'd much rather be looking at the thing at the right of the screen, because it has that first property of Pandas, transparency. You can look at your data at a glance and understand it very quickly because it's got that clear tabular representation plus the nice integration with Jupyter Notebooks. You can see there's one row for each output of the model. There's one column for each characteristic that an output can have. In this case, the model's finding triples of subject, verb, and object, and it's all there. Whereas if you look at the left, all that jumps out to you is, yes, that's JSON data. Everything okay? I'm getting a lot of word in the chat. Okay, it looks like things are okay on the internet front. So let's continue with the demo. So we had a second model that we're trying to combine together to find all these quotes from executives, and that's the model that finds outputs of mentions of people by name. Here's what that output looks like. Again, we can translate that to a data frame, and it becomes a lot easier to understand because of that transparency. Now, as I mentioned, there are three aspects of Pandas that I want to show: transparency, simplicity, compatibility. Let's talk about simplicity for a moment. When you do data analysis with Pandas, there is a wide variety of high-level operations that you, there's a problem with the demo. Can't see the right-hand side of the screen.
The screen updates are a little slow or glitchy.
Okay.
So when things change on your shared screen, we're not always seeing all of it.
Got it. Okay. Are you seeing the person mentions data frame now?
I still don't see it. So try unsharing and resharing and see if that works.
Sure, no problem. Sorry for the technical difficulties here. How is that looking now?
Yes.
Better. Okay. Hopefully this stays running. If not, we can do the same trick again. So as I was saying, when you translate a model, the raw model output to a data frame, it instantly becomes a lot more transparent. You can see at a glance what is going on. At least some of the audience can see at a glance what's going on. Sorry, Eyal. Not sure what's happening there. But what about processing this data? So before, when we were going through the PowerPoint slides, we had to invent this algorithm to combine the outputs of these two models and find where they match up, right? And by the way, this code, if you run it, does run. It produces more JSON data. Well, here's what that looks like if you're using data frames. It's one line of code, because Pandas comes with a large variety of high-level operations that you can mix and match and combine together like Legos and building blocks to make your application. And so a lot of operations like joining two data frames, you just call it the appropriate join function instead of having to invent a join algorithm. Now, if you look here, you'll notice that there are actually I probably shouldn't, there are two quotes in this document, but we've only found one. You can see these in the someone said something at the top. There are two executive quotes, but we only found one executive. And that's because our person mentions model was not trained very well for this domain. So we need to switch to a better model. And here we have the output of the Watson natural language understanding model for person mentions, which works better in this domain. It's a different format, but if we translate that model to data frames, it looks very close to what we had before. And in fact, this is and by the way, it's got all of the, it's got both people, this executive that's in a quote, this second executive that's in a quote, and this person that's not in the quote. And we can run the same exact line of code to combine these outputs of these two models. This is what we had before. We just change that, replace one data frame with another, and the same code just works because data frames have this property that I call compatibility. If two libraries produce data frames as those outputs, as their output, then those outputs become compatible because they're both data frames. You can operate over them using the high-level operations that come with Pandas, and it just works. Whereas if we take our algorithm from before that we had written to process the raw outputs of these two models, and we try to run it with the Watson model's output, well, you just get a stack trace back because this algorithm hard-coded aspects of the data structure. So to summarize, and I'm going to attempt to switch my screen back to PowerPoint. Hopefully we can see that. If you're not seeing my screen, I cannot see the presenter view, by the way. Just speak up, one of the other co-presenters here. So there are three reasons that we would want to use Pandas on NLP data. Transparency, in that you can see at a glance what's going on with your data. Simplicity, in that we have high-level operations we can compose. And compatibility, in that the outputs of different packages become compatible with each other as soon as they're translated into data frames. And this makes all of the data analysis tasks inherent in any NLP workflow go a lot easier. So you really should be using Pandas if you're doing natural language processing. Now, if you're one of the people in the audience who maybe already is using Pandas for natural language processing, you're probably thinking at this point, wait a minute, you can't do that with Pandas. All that stuff that you showed, you can't do that with Pandas. And to be honest, you'd be a little right, because with Pandas out of the box, the functionality that I just demonstrated is actually not quite possible, because you need to add some extensions to Pandas to make manipulating those kinds of NLP data that I showed work in Pandas. And we at IBM have released an open source package containing extensions to Pandas data frames that we have very creatively named Text Extensions for Pandas, which is an open source library that adds enough additional functionality to Pandas to be able to use data frames end-to-end in the NLP applications. Specifically, we add new data types to Pandas, we add new operations over those data types, and we add integrations with common NLP libraries. This is an open source library. We have source code available on GitHub. It's also available as a package pre-built on PyPy or Conda. And this library is built on top of the extensions facility that has been available in recent versions of Pandas data frames, where the central extension point that appeared around Pandas 0.23 is a class called extension array. And the basic idea with this extension point is if you make a class that extends extension array, you can create the backing store for a new type of data in Pandas data frames, and your new data type will get all of the functionality that a built-in data type would get: the efficient in-memory storage, the high-speed vectorized high-level operations, fast binary I/O for saving data to files or transmitting data frames over the network in your distributed system. That all comes for free as long as you implement all the hooks in extension array. And many of the built-in types in Pandas actually use the extension array mechanism. In text extensions for Pandas, we add two types of new extension types to Pandas to cover two very important concepts in natural language processing: spans and tensors. Now, spans you've kind of already seen in the demo I just showed. We have this data frame containing the results of the Watson natural language understanding person mentions model. And this column person actually contains span data. Every cell of this column contains a span, a region of the target document. In this case, the string version of that shows the location in characters and the covered text. But internally, what we're storing behind the scenes inside this data frame is a span array object that extends extension array and stores these spans efficiently using a pair of dense NumPy arrays. So we can do all sorts of operations very quickly. And because this is a Pandas extension type, all of the stuff that you would normally do with a Pandas series just works. So for example, I didn't show the code that produced this data frame, but that code looks like this. It's just a series of operations. We started with a data frame that contained all sorts of what are called named entities, persons, organizations, locations, and we filtered that down to just the person mentions, and then we did some adjustment to the column names. All of the operations you would normally do with a Pandas data frame series just work on extension types, and we can leverage that to get a huge variety of operations. And we add additional ones, like I'll show you in a moment. The second extension type that we add to Pandas is one for storing tensors in the cells of a data frame. Tensors, or n-dimensional arrays, or as they're known in NumPy, ND arrays, are a very crucial part of modern natural language processing models. Modern NLP relies heavily on deep learning, and deep learning models use tensors for their inputs, for their outputs, for all of their intermediate data. And our tensor data type allows you to store tensors in each cell of a Pandas data frame, but to have that entire series backed by a single dense NumPy array, which allows you to have very efficient operations over all that tensor data. And we can use these tensors to store a number of the inputs and outputs of models, which in the case of natural language processing is often like the thing we see at the right here, word embeddings. An embedding is a dense vector representation of the information inherent in a region of your text document. And this is a much more convenient representation of that text for a model to operate over than the original text. But you can also store things like n-grams. If you have a NLP application that involves optical character recognition, you can store image data in tensors with this extension type. And because it's a Pandas extension type, you get all of the built-in operations, and it also is implemented very efficiently with an internal single array that stores all of those tensors in one shot. And by combining these data types together, you can build out complex data structures as data frames, not bespoke Python classes, so that you can do, for example, create a data frame where you have one line for every word in the document, and you're using a span column to store the location of that word in the document, and you're using a tensor column to store the embedding of the neighborhood of that word in the document, and you have other columns in your data frame that store other attributes. And you can see how you could use a data frame like this to train a model or to evaluate a model. You can do every step of your end-to-end NLP application in Pandas, using Pandas to cover every step of the way. On top of these built-in mechanisms, we also have domain-specific operations. So beyond the built-in things that you can do with the Pandas series, you can do domain-specific things like span-specific operations. In the demo I showed you our containment join that takes two sets of spans and find the cases where one span contains the other. For tensor data, we can do tensor-specific operations. Almost anything you can do with the NumPy array, you can do over the tensors in the tensor series. And we also have facilities for getting data into these extension types, or rather translating the output of common NLP libraries into data frames that use these extension types to represent the common NLP concepts, or for taking data frames containing spans and tensors and serializing, deserializing those to efficient binary formats to write to disk in Parquet files to pass over the network with your favorite distributed system like PySpark or Dask Array. And by tying all of this together, specifically looking at the Watson natural language understanding, we can build end-to-end applications like the one I just was showing you earlier. There is actually a more complete demonstration of this. How am I doing for time? 23 minutes in. But there's a more complete demonstration of this, which I think I will skip running through the notebook so that we have more time for questions, where basically we go end-to-end in this application, find this pattern that I was showing of the executive being quoted in the document indicating that that person is an executive. And we go all the way from taking the outputs of the Watson natural language understanding models for finding named entities and semantic role labeling, to building a function that will mine this pattern from a document, and we apply it to 191 documents and mine the names of 301 executives. And we can build this kind of end-to-end application using Pandas for every step of the way. So at every point in the process, you have a Pandas data frame that shows your output very clearly, and you can do every stage of processing with high-level Pandas operations. So I would encourage you to take a look at that notebook. There's a list link at the bottom here to both the notebook version on our website as well as the blog version of this use case that goes end to end. So at a high level, though, what I've talked about today is our open source library, Text Extensions for Pandas. This is a new open source library from IBM that extends Pandas data frames to be able to represent core NLP concepts with data types and core operations over those data types, and to be able to translate the outputs of common natural language processing libraries into Pandas data frames so that you can build applications that manipulate NLP data and do all those manipulations in Pandas, because it's a much more literate way to do the data processing that is inherent in natural language processing applications. If you'd like to find out more, I would encourage you to go to our website. The link is at the bottom. It's ibm.biz/text extensions for Pandas. And now I think we have a couple minutes that we can take some questions. I'm going to stop the screen share so that I can see the questions. So thank you for all the clapping. That's very nice of you.
Thank you so much for this great talk, Frederick. And if you have questions, you can post them on the Q&A tab on the right side of your screen. And you can upload questions that you would like to be asked. And we have a few minutes to get more questions for Frederick.
If we don't have immediate questions, then I can probably share my screen again and walk through that demo notebook that I had to skip over.
Yeah, sure. We have a few more minutes. If there are no questions, yeah.
Let me put that part of my talk back into my talk.
Okay.
Well, there is one question about what is a good way to start diving for a newbie. And my initial answer to that would be maybe take a look at what we're going to show here, which is our end-to-end market intelligence use case. There is a blog version of this, which you can find on Medium if you look at the IBM Data and AI blog. And this is just showing how you can build end-to-end an enterprise-level application of natural language processing text that extracts useful information from corporate press releases. And as I mentioned earlier, we're looking for this pattern here that I'm showing, where the press release quotes an executive by name, and we're going to find that pattern by combining the outputs of two models. In this case, we're using models from our Watson Natural Language Understanding product. This is a web service that you can call. You get about 15,000 requests per month for free, and you can call it through a Python API. And what we basically do in this demo notebook is we start out with the raw output from the Natural Language Understanding Python API, and we use Text Extensions for Pandas to convert that output into a data frame. And instead of having to deal with a lot of JSON, you immediately get this very literate version of all of the pairs of subject, verb, and object that this model found in the document, which we can then filter with one line of code down to all the pairs of subject, verb, and object, where the verb is some variation on the word to say. That is, all the instances of somebody said something. And then you can see from this data frame that we're getting exactly what we want. We're getting these quotes from different people. And then we want to, of course, extract out the names from here. So we run another model, again from Watson Natural Language Understanding, that extracts out what are called named entities, persons, organizations, locations. And again, with one line of code from our library, we translate the output of Watson Natural Language Understanding into a data frame. So you can see at a glance what is going on in that output. And then from there, we can filter down to just the mentions of persons. And now we have all the person names. And because we have a span type in here, we have the locations of all those names in the document. And now we can take those two sets of model outputs, and with, again, one line of code, by doing a join between these two data frames, find all the places where those two models line up. And we have all the places where in our example document, a person is quoted by name. And then if we take these little snippets of code that we've built up interactively in the notebook and paste them together into a single function, which we have here, find persons quoted by name, then we can build an end-to-end data mining application where we call that function on, in this case, 191 IBM press releases, stitch the results together, and we get a data frame containing the names of 301 executives. And you can see here, hopefully, that it's really easy to build up a end-to-end application using data frames without getting lost in all the minutiae of exactly what part of your JSON data is representing what part of your model output and having to invent algorithms over and over. It's much easier, a much more literate way to do the data manipulation that's inherent in building an NLP application. So again, that's text extensions for Pandas, and this is our market intelligence notebook. It's inside our repository at tutorials/market if you go to our source code on GitHub. All right, and we are running close to the end.
Yes, we're almost out of time. There are a couple of questions, but you have partially answered one of them. What is the best way to implement the Watson NLP tool? Is it free? You kind of mentioned we have like a credit that we can use for free, but
right, you can create a light instance, and that gets you 15,000 requests per month. And if you need to go beyond that, it's easy to upgrade to a standard instance. And as far as what toolkits our extensions work with, we currently have support for natural language understanding, Watson Discovery, Spacey, and limited support for this Transformers library. And it's actually quite easy to take the output of another library and translate it into DataFrames, because DataFrames have a lot of other facilities built in for building new DataFrames. But we have built-in support for those 4 libraries already, and we're constantly looking at adding additional ones. And an additional question is, what is the maturity level of all NLP models to understand text today from my experience? And I would say that it really, really depends on the task that you're looking at. So for example, we've talked about 2 kinds of models here, named entity recognition and semantic role labeling. Named entity recognition is a much more mature domain. You can expect a named entity model to work out of the box. Semantic role labeling is much more difficult. You can expect basically to have to get something from a vendor to get a ready model in that domain. So different sub areas of NLP have widely varying degrees of maturity. I think those are the main questions that are on the
right, and I think we're at the end of our time. Thank you so much, Frederick, and for this great presentation. And I personally am very excited to try it as an NLP practitioner and Pandas lover. And thank you.
Thank you, Batman, and thanks to all in the audience.